Alright gang, here we go. This is for Chem 2 Unit 8. We're going to talk about colloids, suspensions, lots of fun stuff. Alright, colloids are a new type of solution that we haven't really talked about much. Okay, they have some interesting applications, but they don't have, we're not going to deal with them a lot later throughout the rest of the semester, so we're not really going to spend a whole lot of time talking about their individual particular qualities and so on and so forth. But suspensions are made out of particles that are larger than individual ions or molecules, but they're too small to be settled out by gravity. Okay, so they still look like solutions, but they have very particular properties. Okay, and we can have all sorts of different types of colloids. Okay, so we can have gas, liquid, and solid colloids. Okay, and there's always two parts to it. There's the dispersing substance, or the thing that's solvent-like. Notice that it's not actually a solvent. We define it as solvent-like because it's the thing that's more abundant. Okay, and then there's also the dispersed substance, or the thing that's solute-like. All right, and we can see that we can combine these things, so gas, liquid, gas, solid, and then flip-flop them, and we get different types of colloids. Okay, gas is not a colloid at all. Okay, because it's a solution, right? And we've talked about this, how they mix completely. Now, gas liquids, these are aerosols, like fog. Like if you've ever been outside on a foggy day, the dispersing solvent is the air. It's a gas, but there's also liquid water, vapor that's in the air, and it's being spread out, and it's an aerosol. It's fog. If there's a solid that's spread out in the air, it's still an aerosol because it's out in the air, but it's called a smoke. All right, it's smoke, right? So it's kind of fun, or not fun, but when you're, out camping and you're burning wood, whatever, and you get smoke in your eyes. Okay, those are actually little pieces of carbon that's come up and hit you from the incomplete combustion reaction. Kind of fun. All right, liquids with gases is a foam. So whipped cream. So when you've had your pie, you put a little bit of whipped cream on it. There's your foam. Liquid with liquid is an emulsion. Okay, we're going to talk more about emulsions coming up, and so that's like milk. And then liquid solid is a sol, and this is paint. Okay, so especially like house paint, latex paint this is a great thing here. Okay, solid gas, solid foam, so like marshmallows, solid emulsions, butters, ruby glass, solid with solid. It's kind of like an alloy, but they're slightly different. All right, now one of the interesting things that you can use to identify whether or not we have a colloid is by whether or not it exhibits what's called the Tyndall effect. All right. So this solution here is just a regular solution, but this guy here is a colloid. Now notice that the light travels through the solution, no problem, doesn't get affected. It just kind of keeps going. It just makes it generally just a brighter solution. But on the colloid one, you can see specific place where the light traveled through, and that is the Tyndall effect. And the reason it happens is because the colloid is full of particles that are slightly bigger, and sometimes quite a bit bigger than the atoms and molecules that were in your regular solution. And because they're bigger, they actually scatter the light, right? They'll actually scatter that light, and so you can see the path that the light takes through it. And so that's the main way of identifying whether or not you formed a colloid, is if it scatters these rays of light as it moves through. Okay, colloids have lots of interesting applications. Okay, and so this guy here is a colloid, but notice that we've got some areas here that are polar and nonpolar. They've got they refer to them as hydrophilic ends versus hydrophobic ends. Hydrophilic ends, the philic means loving, and then the hydro means water, so it's a water-loving end. And then the nonpolar end is the hydrophobic end, right? And we remember from before, like dissolves like, so the polar parts are going to dissolve with the polar ends of the molecule, and the nonpolars are going to interact, or not going to want to dissolve. Okay, so essentially when you get these large molecules of colloids, what happens or these large groups, is you have they'll rearrange themselves, so all of the polar ends will be on the outside and all the nonpolar ends will be on the inside. So if you've taken biology and you remember what that was like, it kind of looks like a phospholipid bilayer, right? It's not nearly as organized as that. This is just kind of like a clump of things that happen to stick together, but it's kind of the same idea. Okay. All right. Stabilizing colloids by adsorption. Okay, so we can kind of get colloids to dissolve more readily or be able to make smaller particle sizes by using ions. Okay, so we can add extra ions to this guy. And those ions we're going to stick to the sides of our hydrophobic, right? And so here we've got the hydrophobic particle. Okay, on the outside we've got these negative anions that it's adsorbed, right? They stuck to the side of it. Okay, and these will actually interact with the aqueous solution here. So you got your cations and then these negative particles here, and they're going to stick together. And so essentially what happens is because the negative goes on both sides, that they repulse one another, and so that they won't stick together. If this wasn't happen, these two guys would hit each other, and the hydrophobic ends would attract one another, and the hydrophilic ends would get stuck to the outside, and you end up with one big chunk. So you end up with and eventually, if these things keep growing, then gravity will start affecting it, and it'll fall out of solution and won't be a colloid anymore. You'll just have like a chunk of gunk of whatever it is at the bottom, whether it was a solid, a liquid, or a gas. All right, colloids and biological systems play an important role, and we call this emulsification. Emulsification, essentially what that means is you're going to add some new compound to it, all right, that is going to help your colloid or your particles dissolve in the water. Okay, and so emulsification has lots of applications. We like margarine is essentially emulsification of like because the margarine is fatty, but then there's also water in it, and so you get these two. Using emulsification can get them to actually mix together. Okay, and so that's an important application of emulsification. We also talked about milk earlier, at least had that as an example. You know, milk doesn't separate itself out, but it's it's water and then a bunch of different fats, right? And fats are essentially nonpolar, but by adding emulsifiers or having emulsifiers present in the milk, it allows the fats to dissolve in the water, and so you get a colloid as opposed to just a separated gunk that you have to shake up. So for example, you know, everybody's had like, or at least seen Italian dressing. Italian dressing has some parts that water and some part is the oil, and then usually a bunch of other stuff that's in there. But in order to use, effectively use your Italian dressing, you're supposed to shake it up. By shaking it up, you are emulsifying it. You're adding energy to create this thing to make a colloid in there. But because it's not permanent, what you've done, it'll eventually separate itself out again. All right, last thing here is this idea called Brownian motion. Now, Brownian motion is named after this guy. I don't remember his first name. Brown was his last name. Surprise! And before we really understood the motion of particles and kinetic molecular theory and so on and so forth, he witnessed through a microscope the movement of particles, and he noticed that these particles that he could see through the microscope. Now remember, we can't see atoms and molecules with a microscope, and so he saw these particles in there, and they would sit there and they would bounce around like crazy. Like imagine what you're looking at, and you see these things, and they just kind of look like they're going around like nuts, and they're not going in one specific direction, and then nothing that you could see hit them, but suddenly they change direction. And so this was defined as Brownian motion, because it was like, well, what is going on here? There's something else at work. We're not quite sure what it is. And eventually, we now know that what's happening to those bigger pieces that we can actually see with the microscope, we can actually see and we know that they're getting hit by smaller particles that we can't quite see, and they're surrounded by these smaller particles on all sides. So as they get hit from all sides, it kind of changes their path around. Okay, and we can actually see this pretty easily in Brownian motion, like if you just by looking at fog or smoke, so on and so forth, we can really see Brownian motion at work fairly easily. All right, Now, this last bit here is called the calculated mean free path. Essentially what this is, the mean free path is the average distance between collisions. Okay, and so here's the radius of our spheres for our colloids in nanometers, so 1 nanometer, 1,000 nanometers. Notice that as it gets bigger, okay, the mean free path gets smaller, right? Because it's bigger, it's going to get hit more often, so it can't go farther, or it goes less far before it gets a collision that changes its course, okay? And so this motion is due to these collisions, right? So that's that Brownian motion, and then that's mean free path. We don't really have, we're not going to do much more than that with it. I just want you to kind of be aware of the properties of colloids, what's causing them, emulsification, Brownian motion, so on and so forth. All right, so go ahead and do your homework. Let me know if you have any questions, and I'll see you on the flip side.